So, I want to start with a little bit of post-mortem on the discussion from a week ago, from last Thursday. For one thing, we got into some calculation of this focus towards the end, and I'd just like to try to clear up some of those calculations. I have some other comments over there. So yeah, what I was trying to do last time is I was trying to avoid getting caught up in gritty calculations. And I didn't completely succeed. So let's try and state sort of rule that I was trying to state without getting into the gritty calculations. And then maybe I'll try to point out where, when we started writing down the calculations and getting into the gritty part of the calculations, where we may have stated some incorrect formulas. And I think one of the things that was a bit of a red herring was we got into a big fight about when you multiply matrices, sort of, I don't know, horizontally or vertically or something like that. And I think that really was a red herring. I think it was just something that we got caught up in because we were trying to figure out where we were making a calculation mistake. And I noticed that on Tuesday, John was talking about things like matrix multiplication and things like that. And he was just, he was doing it the bizarre way. He was doing it my way, which I don't know how to describe it. I just know that it's different from a kind of way everybody else does it. So I don't know, that's some evidence that you can do it the bizarre way without getting into too much trouble. So let's see. So the what's that?
Then something.
Say it again?
We just have labels of them. R,
okay.
B, R, and B.
Okay. R, number R,
Number B.
number R1?
No, just R. Use prime. Use prime. Number of R, number of red.
Oh, red, okay.
Number of blue.
Okay. Number of red, number of blue.
Number of red prime.
Number of red prime. Number of
Red prime.
red prime. Number of blue prime. Number of red double prime. And we have these constraints, you know, so that A plus C has to be equal to this. So, so for example, this number here is representing a Young diagram with two rows. And in the first row, there's number of bar boxes, and the second row, there's number of boxes. That's where you can kind of interpret what's going on here. And now, the answer I stated is that when you compose these Hecke operators, and again, let me emphasize that we're talking about Hecke operators here, but what we're doing here is we're only talking about one particular kind of Hecke operator, and it's not even the kind that people usually mean when they talk about Hecke operators. but this is a kind of Hecke operator that we're talking about here. I mean, there's notation for it, this matrix notation for it. And we're thinking about composing these Hecke operators, and I'm not trying to do an exact calculation right now. I'm pointing out that there's a sort of interesting approximation that you can do to calculate the composite of these Hecke operators. And it comes out to be that you multiply these matrices together. It's like a sort of funny normalization matrix in the middle. And this would be 1 over the number of R prime and 1 over the number of E prime. And whatever this comes out to be when you multiply it out, that's the correct answer. That's all I really meant to say. So I think some people were doing the calculation of getting the right answer, and I wasn't really following exactly what calculating. So this is all I'm really trying to say. This is the right way to do it. And as far as what? Yes, but I don't even think there's that much potential for confusion in terms of the.
Well, because I mean the R prime and D prime are, it's not symmetric with R prime and D prime. The first one, R prime and D prime are the rows. The second one, the R prime and D prime are the columns. So you have to be very specific about.
Okay, but there's probably more than one correct way. There's probably several different ways of getting the conventions to work out correctly, and I won't try and state them right now. I think it's actually kind of obvious if you think about how the problem works. But again, it may be that I'm not even sure, but it may be that I'm using some strange convention that's a little bit different. And yeah, so
We can use probabilities.
yes, and but another point I'm trying to make here is that there are all sorts of confusions that you could get into here as far as how to do the calculation and interpret the answer. But actually it's not that bad, because you have to remember that these matrices of numbers, these are counting numbers. They're telling you something very specific. They're not just like real numbers or something, they're counting numbers. And so when you get the answer, it's sort of very unambiguous as to how to interpret that answer. You don't have to worry about like normalizing it in some funny way. It should be obvious how to normalize it, because the answer, the numbers have to add up like this, for example. Sorry, R, number of R, number of E, number of R, double prime. Say it again?
Right.
I'm talking about prime and so forth.
I'm sorry. I screwed up. Sorry. What I
You want the product.
I guess that when you get the answer.
When you get the answer, that's
Yeah, when you get the answer, it'll look like this. I don't remember exactly. This is the part where I sort of trust some people's calculations better than my own. But whatever it is, it should add up like this. Okay. So the lesson of this is supposed to be that what we're doing here with these Hecke operators is, in some funny sense, an imitation of ordinary matrix multiplication. It's an imitation of ordinary matrix multiplication. And last time I was trying to emphasize how similar it is. But right now, I should perhaps try to emphasize how much of a contrast it is, because it's an imitation, but it's a weird imitation. And right now I just want to emphasize some of the ways in which this composition of Hecke operators is different from ordinary matrix multiplication. So let me just list a few of the really obvious differences. So
You have a third matrix in between.
that's not even that big of a difference. Because again, that's some sort of normalization thing, and that comes up in ordinary linear algebra sometimes. You might not notice it. Sometimes when you need normalization factors, like when you're doing statistical mechanics or things like that. And it often takes that form in linear algebra that you're interposing a diagonal matrix in between. Well, anyway. So I'm going to offer a contrast here between ordinary matrix multiplication and the weird imitation of it that we're studying at the moment. And I'll just call that weird for the moment.
Why are you not using the C word?
Because I haven't. I'm not going to say what that yet.
Okay.
So I guess the really the big difference is this. So with ordinary matrices, we make an algebra where the matrices are the elements of the algebra, Whereas with these weird matrices, what we do with them is we make an algebra where the matrices are the basis elements of the algebra. And that's a very different thing when you think about it. Right? So the basis elements, an algebra is a particular vector space, so that vector space can have a basis. And that's what we're doing here. We have what we have is essentially what we're doing is we're making an algebra out of Hecke operators. But these matrices are just the basic Hecke operators. So the whole vector space the whole algebra is a vector space with these matrices as the basis elements. And that's very different from what you do in ordinary linear algebra, where you just have an algebra whose elements are matrices.
But you can multiply two basis elements and to get another basis element, right?
Another linear combination.
Is that right?
Let's see. I don't think that's right. That's sort of like the second thing that's weird. The second thing that's weird, but it really goes along with this, is that multiplication over in the ordinary situation, matrix multiplication, is, just a well-defined operation. Whereas over here, the weird matrix multiplication is sort of fuzzy. I mean, the result is not a single matrix. if you take two basis elements, those correspond to matrices. You multiply them together, and you don't just get a single matrix. Although I've been emphasizing over here that you approximately get a single matrix if you're in a situation where the law of large numbers kicks in. Remember, that's what I'm saying about this calculation. That is, this is just an approximation. And it shows that approximately, when the law of large numbers kicks in, when these numbers are big, approximately you get the composite of these Hecke operators to be just a single matrix gotten by a process that very much imitates ordinary matrix multiplication. But when we were calculating this last time, a lot of you were pointing out that when you actually do the calculation very carefully, you don't get just a single relationship for the answer of how to compose two relationships. You get a sort of superposition of different possible relationships. And I'm just emphasizing the most likely relationship, kind of where the probability clusters is near this relationship. But one of the big differences is that matrix multiplication in this context is fuzzy, although you can just really think of that as meaning that instead of getting a binary operation, a well-defined binary operation, what we're getting over here is, a bilinear operation. Right? A bilinear operation expressed in terms of a basis, you can sort of think of it as like a fuzzy operation in a certain sense. Like the structure constants are sort of telling you sort of like the probabilistic weights. If they're the right kind of numbers, positive numbers, the probability, you sort of think that the structure constants of a bilinear operation, you can think of them in certain contexts as describing a fuzzy operation on the basis element. And that's sort of what's going on here. So, so that's supposed to be the lesson at this point. That this composition of Hecke operators is an imitation of ordinary matrix multiplication, but it's a weird imitation. I was really trying to point out here some of the ways in which it's really different. And there's really a lot more to say about this. There are other important things to say about how the composition of these Hecke operators relates to ordinary matrix multiplication. But instead of getting into that right away, I'm going to describe something a bit different first. I'm going to describe another system of notation for representing these Hecke operators, these relationships. And just as this system of notation is supposed to be suggestive in one direction, this new system of notation is supposed to be suggestive in a slightly different direction. So, so I'll call this next system of notation, I'll call it braid notation. And let me try to describe how it works. So, it's supposed to be another system of notation for representing the exact same thing. We're still representing these relationships between flags. That's what these matrices represent. They represent relationships between flags, or Hecke operators between flag representations. And now I have another system of notation for representing the exact same thing. And I'll try to describe how it works. And I guess I'll describe how it works by going via the matrix notation as an intermediary. So I'll draw a matrix of the kind we talked about, and then I'll show how to change that matrix notation into the braid notation. So here's a matrix. And again, it's a matrix of natural numbers, of counting numbers. And I guess to sort of dramatize how it works, I'll make these actual specific numbers.
Oh, we're really regressing here.
What do you mean?
That's a very old notation.
Very old notation?
Or you can say the categorify.
Yeah,
It's
it's,
not finite.
right. It's somewhat of a categorification flavor of it. So it's 4, 3, 2, and 4. And now, so let's see. So I mean, this one is that, and this one is, did I get that right? And this one is that. Okay. Up here at the top I have 6 dots and then 7 dots. So I'm going to put 6 dots here and then 7 dots here. Although in some sense, I'm not really sure how categorified this really is. Because these dots that I'm drawing, like little particles or something, in some sense you should really think of them as being like bosons. Bosons is a kind of particle that physicists talk about, which are distinctive for the fact that you sort of can't tell, it's very hard to tell one boson from another one at the same time right next to it. And maybe that's true, these little black dots. They don't have very much personality, one from the other.
Well, the line in the middle there gives them, the left one to the personality red, and the other right one has personality blue. Right?
Yeah, I guess that's right. Yeah, this one, red.
This is red prime.
And let's see, so over here, it's 7 over here. And now, the way we draw the picture is at the top of the picture, you should sort of read the matrix columns first. So it's like you're reading this column, you're reading this column row by row, and then you're reading this column row by row. At the bottom of the picture, you should read the matrix rows first. So you read the first row, column by column. And then you read the second row, column by column. So, and then you sort of connect the dots with these braids or strings or lines or whatever in the way that fits with what I said. So these first four here, I guess this is the first box, whether you're in row first or column first, this is still the first box. Those four connect up like that. And whether you're reading row first or column first, this is the last box of the four boxes. So it's going to be 4 at the end. So now for these 5 dots in the middle, 1, 2, 3, 4, 5. Yeah, if you're reading column first at top, yeah, then these come before that. Yeah, so that's the picture. Now, I just did this for a 2x2 matrix, but you're supposed to get the idea of how it would work in general. No matter how big the matrices are, you still have, at the top, you're sort of reading the matrix column first, and then at the bottom, you're reading the matrix row first, and you're connecting the dots in the way that makes sense, like that.
I'm curious about whether everyone
Can do that.
understands why this braid is just a picture of the relation that the Hecke operator
Like R, B, R prime, B prime, then.
it could
Yeah.
be completely clear. I have no idea.
Okay,
It
well,
doesn't give me such a sort of,
okay, let's talk about that.
he's sort of like Marcel Marceau, drawing this thing without saying much about what's actually
No,
going on.
Okay, let's try and think about that then. So the story that I gave about this, I guess, is that the unprimed stuff, you can sort of think of these little dots as being people. They're the same people at top and then at bottom. And so in some sense, it's like the world line of one of the people. And
So if you want to, when you were talking yesterday about the first one being the fact that they have red hats on.
right, this is a hack.
Being the
And
fact that
this
it's
looks
like
like a
red
hack.
shoes.
This is his head, and this is
Right, so we'll call these red shoes or blue shoes.
right. So these are people with red hats, and people with blue hats, people with red shoes, people with blue shoes. And for some reason, I don't know, all the red hats have to put it that way, and all the blue. So some people are sort of caught in the crossway. And
Are you thinking braids as the people?
say that again?
These braids as the people and red hat and blue shoes?
Yeah, I mean,
Yeah, so it
I mean,
sounds like this, each one is wide as a person, is a single person, and it represents that, if we look at that person in terms of the first characteristic, they're over here. In terms of the second characteristic, they might move, they might stay in the same place as we rearrange the people.
Yeah, I mean, it's really a very vivid picture. As I say, the people are actually these little, skunks. This is their head, and this is their foot. But perhaps instead of thinking that, their hats are red and their hats are blue and their shoes are red or their shoes are blue, for some reason in this picture it's more a matter of where your head is and where your feet are. So some people are, leaning like this.
I always think of it more as,
Yeah.
you've got these things, people divided up into groups, which are like rooms, so there's like the red room and the blue room, and there's this division at the beginning of the day and at the end of the day, and time passes as you move down this picture. So some people stay in the red room, some people switch, and this matrix describes different possibilities.
Right, so that's one of the things people do, one of the things physicists do with pictures like this, interpret a certain dimension as a time dimension, and this is like a process happening over time or something like that. Okay, and so what do you say, the red room and the blue room, and you know,
The particles in the red state, blue state.
So this is still the red, blue, Riverside, and time.
yeah, the prime just means that they're time.
Right, gotcha.
So that's how you interpret this. And, all right, so in what
So
way?
you want to write a R and a B and R prime and B prime.
Over here?
Yeah.
R, red and blue, and red prime, and blue prime.
Now I'm sure it suggests to how this notation, the matrix notation fits with that notation.
Yes, yes. Okay, so in what ways is this particular notation suggestive? Well, one minor way we could suggest it is, again, that it really does hint at some sort of categorification, or perhaps I could even emphasize some sort of discretization. I mean, just like the matrices in terms of numbers, you know, these are numbers over here, A, B, and C, D. They're counting numbers, which actually represent sets, but somehow, you know, introduce the idea of numbers. Numbers just measure things. But really drawing the set of dots really emphasizes the discreteness that's going on here. So, I don't know, that may turn to be more clear. But,
It's kind of like instead of being just a number, it's really saying it's a collection of 6 points.
yeah, yeah. Okay, I guess I may as well admit that I'm sort of secretly hinting that this discretization may in some way relate to the original concept of what quantum was supposed to mean in quantum mechanics. You know, quantum mechanics, like Planck invented it, I think he invented the name quantum. Quantum was like discretization of something. I'm not trying to say anything intelligent about that. I just want to admit that I have some ulterior motives about this. But there's something else that's suggestive. There are other things that are suggestive about this notation. Say it again?
It's for you, right? If you're thinking of these the same for these people.
Yeah, I mean, okay, if I understand what you're saying, so Hecke operators are based on representations of some particular group. And in this case, the Hecke operators that we're dealing with have to do with the representations of the group 13 band. And this kind of picture has a lot to do with, you can think of it as a picture of something like an element of the group 13 band. Although it's actually a little bit more involved. It's supposed to make you think of a picture of a sort of superposition of a whole bunch of elements of 13 band. The idea is that because these 6 guys here are sort of clumped together, you're sort of not really supposed to know how these guys might be commuted among each other. It's like they're allowed to secretly commute themselves any way they want without telling you about it. And same with this clump over here. And same with this clump over here and this clump over here. But aside from that, you know, the individual, the clumps are not allowed to sort of commute with each other. So it's like we're getting some information about the order in which these things are lined up, but we're not getting complete information.
Do we have more information than that though? Okay, sorry. When we include these tabs, we then kind of said, well, in fact, these 4 over here really were the 4 that go down to this. and these two were the two that are going to switch to. But we don't know anything about the comparison between those ones. So maybe we have more information than just these 6 compared to between each other. We don't know about it.
Yeah.
But we really know that with this direction, now we know that these 4 can change places, the first 4, and these 2 can change places, but they can't interchange.
And just say 6, so dividing the 6 factorial is saying divide by 4 factorial, 2 factorial.
Okay, there may be some
More
issues
stuff.
that involve there that I haven't completely, but how come I different about again, some of these normalization issues?
And maybe I'm reading more into the information we have, like you say, but it, you know, so if you just ripped that first line with the 6 dots and 7 dots before we wrote that, then yeah, it's clear we don't know what the difference is between those 6 dots initially. But once we have this matrix that tells us how it takes us to this other line, we kind of have more information about those dots all of a sudden.
But it's really supposed to tell you, I don't think it's really supposed to tell you which 2 of the red guys turn blue. But it's very hard to draw a picture of 2 red guys turning blue without making it look like specific ones did.
Yeah, I'm very ambivalent about this idea of making these things seem like individual dots.
I may be reading more into this than there is.
Yeah, and I'm not sure how much we should read into it. I'm very ambivalent about fixing these things as individual dots, because in some ways they sort of have some individuality, but in some other ways they lack individuality because they behave in a so-called bosonic way. So I don't exactly know how to respond to what you're saying. We'll have to learn more about that as we go along.
Can you think of this element right here as image of a permutation from 13 bang in 13 bang modulo the subgroup corresponding to the Young diagram? With
Something like that may work also. Like it's some sort of coset. Well, it probably is a double coset secretly. I don't think I've ever said that word in this class until right now. I probably should have, because that's the way a lot of other people think about this. So I'm not giving you a good answer to that question either. That's an interesting idea, and again, I'm not quite sure how to respond to
I think the answer is yes.
it. Yeah. Well, what's the yes or no question? I first I've lost it.
Can you think of this picture as describing some equivalent class of permutation?
You can do something very much like that, most likely.
Yes.
Have you mentioned double coset, or do you want to written double coset?
I haven't mentioned them. I've written about
I read that.
yeah.
So, yeah, okay, so as Apoorva said, that's one of the things that's suggestive about this picture, is that it really is getting us close to thinking about the conceptual source that it came from group 13 bang. But there's another thing that's suggestive about it also, or, well, at least there's something suggestive about this name of calling it braid notation. I didn't really draw it very braid-like, because, the idea of braids is that they're actually, I think it's more like a 2-dimensional picture, but the idea of braids is that they have more like a 3-dimensional aspect to them, and in particular, that when 2 of the strands cross, a braid has information about which one's going in front and which one's going in back. And yeah. So there certainly is something very not theoretic going on here. Although, but actually one thing that's a little bit funny about this, yeah, in some sense you should try to draw these as 3-dimensional braids instead of just as 2-dimensional permutation pictures. But one thing that's a little bit funny about it is that the right way to put in the crossings is that you should always just put it in sort of automatically. So there's always one strand coming from the left and one strand coming from the right, and you should always just pick some convention and stick with it. So let's always have the left going over the right. that. Now, I mean, this is good in a way, the fact that it's always going left over right. It's good because,
Not really creating.
yeah, because we're not putting any more information.
We're not creating a bunch of information here.
Right, right. So that's good. On the other hand, it sort of seems bad because it means we're not really getting anything interesting, it sort of seems. Because, you know, to get interesting stuff with knots, you need sometimes it goes one way, sometimes it goes the other way. Kind of like an option. Well, but the place where that comes in is when you start composing. Yeah. Sometimes when you start composing some of these Hecke operators, right? So just like the matrix system of notation is suggestive of how the composition of these Hecke operators imitates matrix multiplication, the braid picture of these Hecke operators is suggestive of how the composition of Hecke operators imitates the composition of braids. What?
In what sense?
Well, in the sense that, you know, when you're another one, you just kind of stick it below it, and you compose, except that you have to think about the sort of bosonic nature. The idea is that these guys sort of are hiding from us through identity.
This is what you talked about, how when we're multiplying matrices before, what we don't get is an exact answer, but kind of like a centralized answer.
Right. So, over here, if you just stuck the braid pictures together, you might think, oh, you're getting a single braid at the end. But it's because of these guys sort of pretending to be one another that you're actually getting multiple possible answers.
Third grade in between, which is some permutation of these guys and permutation of those guys, and you don't know which permutation.
Exactly.
Yeah.
Yeah, and it would almost be suggestive to not compose, to not actually connect this to that braid, to kind of put it directly below it and there's a little bit of space saying
That's right.
there could be a permutation there.
You close your eyes for a minute and don't see the people in the red room trading places with each other.
Right.
Right. And there are some standard notations that I've heard about. I don't know exactly how to draw them, but they're supposed that says that if you put a bar.
A horizontal bar is often used as part of a picture of a braid to mean you symmetrize over the possibilities.
So something like that is going on here, and it's taking place at the interface between the two braids where you're composing.
I was just going to say, it's interesting, because you mentioned how this looks a lot like permutation of 13 bang, because, depending on how you first learn number theory or group theory with symmetry groups, they often write elements of these permutation groups not as the cyclic elements that we spend so much time doing, but as here's numbers 1 through 5, here's numbers 1 through 5, and connect lines in between them of how they permute each other.
Right.
And then composing them, we actually do connect them because we have labeled these points as 1, 2, 3, 4, 5. So it's kind of like a weaker version of that, in that we don't know the difference between those numbers, but we're still doing the same kind of.
I mean, that corresponds to the partition where every one of these is you have n colors for n object.
Yeah.
This is 1, 1, 1, 1.
Yeah.
So everything is very clear.
Yep. Are you going to actually do any compositions of these braids for people? I don't know. Maybe everyone here is much smarter than me. But I just did already taught them stuff so they know exactly what's going on. I would never have understood this idea.
Well, it sounds like they're actually explaining it to me.
I know. It's not fair.
I mean, I'm afraid to actually try a calculation.
Oh, that's what.
Yeah.
I think the braid notation, the great thing about it is everyone can agree what's up and what's down.
Yes.
Yeah,
Because
I'm not going to disagree about composition here.
They can argue about whether it's
I can easily find things to get confused about. If we try to do an actual calculation, I can easily find things.
Okay, yours just threatening us.
Yeah.
You better not do the calculation.
I'm still afraid to do it.
Okay.
We should, absolutely, we should do it. That's my favorite term.
Okay.
So, Okay, but I think we still haven't yet really brought out the importance of the three-dimensional, the third-dimensional aspect of braids. Maybe I should try to ask people to try to guess, say some silly guess as to why it's interesting to think of the braids as these three-dimensional braids where there's crossing information, less crossing over right or whatever. Can you think of a reason why that might somehow come out to be an interesting thing to think about?
What I'm looking at is, if we were to compose a second one here, if we could just compose, I can just compose it with kind of the, I don't want to use the word inverse because I'm going to then say that it won't result in an identity type thing. When we compose it with where all we did is, all I want to do is replace the fact that we're having the same number of elements everywhere.
Sorry, are you suggesting something about this?
Right, so I'm saying that, so these are the things that result in doing this, and so even though something may make its way back to something there where it started, there's no way you can't, enough there that you can't reduce that to two straight lines, because the third dimension kind of wraps one around the other.
Okay.
Yeah, I don't know.
Okay.
I'm just making a third dimensional observation about what happens there.
Okay, that's an interesting idea. That's probably on the right track. But there's something else that I'm sort of fishing for here. Can we think of a way to make the third dimension relevant here to our Hecke operators? Well, I mean, obviously, there's a whole theory of knot theory that's a generalization in some sense where there's a whole concept of braid, which is a very interesting generalization of permutation.
Yeah.
But what in the world might that have to do with our Hecke operators? Anybody have any ideas? How are they
Typically,
yeah.
the symmetric group is a quotient of the braid group.
Right.
That's quotient, I think that you will try to see with that.
That's right.
That's the only relation between braids and permutation. So in this thing that you do there, if you equate it to what Chris was saying, you cannot equate it to a straight line. Then you just get ordinary permutation.
All right. What?
But
Yeah. Okay. Let me get a hint what I'm fishing for. I'm fishing for something that has something to do with Q.
what's Q?
Q is two different things. Well, Q is several different things. Right. Okay. So what is Q?
What's big Q?
So Q is the cardinality of a field.
Okay.
Define a field. That's one thing that Q is. But what's the other thing that Q is? I guess I'm sort of
Non-commutative factor.
Yeah, I mean,
I mentioned it being a phase in some context.
yeah, I'm sort of fishing for cultural knowledge about things like not polynomials that depend on a variable Q, things like that. Alexander polynomials, yes, but even more so the Jones polynomial and the whole family of polynomials.
Partition function.
That means too many different things for me to tell whether I understand what you're saying, but it might be on the right track. Let's see. So what am I trying to say here? I'm trying to say that, right, the first thing I'm trying to say is that, in fact, this third dimension of the braid pictures is actually not relevant for the Hecke operators.
Reason not.
As long as,
Is it NOT?
NOT, it's not, NOT not relevant for these Hecke operators, as long as we're just doing the Hecke operators that I claimed that we were talking about. The Hecke operators that just have to do with people wearing hats and gloves and shoes and things like that.
Because
those
you have to quotient by that relation anyways.
Yeah.
To get the permutation.
So those the Hecke operators we've officially been talking about, and we're talking about this matrix, imitation matrix multiplication and everything, that's all this sort of Q equals 1 case, which, whenever you're doing these, whenever you have like a not polynomial that depends on a variable Q, setting Q equal to 1 is the thing that usually means that you're sort of not really seeing the interesting not theoretic information about which strand is crossing over which strand. So as long as we're just doing Hecke operators for these kinds of groups right here, 13 bang, 14 bang, etc., the third dimension of the braid pictures is not relevant. It's only when the third dimension of the braid pictures starts becoming relevant when we start working with Hecke operators that remind us of the Hecke operators that relate to this group, but that are slightly different. So, I mean, we've been talking about groups like...
Are you going to bring in Hecke algebras into this now?
Well, I've sort of been advocating the idea that Hecke algebra and Hecke operator mean almost the same thing. That you can just think of you can think of Hecke operator as being a synonym for element of a Hecke algebra. So secretly, that's what actually one of the things I've been alluding to all along. So you have finite groups like, for example, GL 13, comma F sub Q. And in some bizarre sense, we pretend that this is actually GL 13 F sub 1, even though F sub 1 is an imaginary construct. So this thing right here is a sort of q-dependent generalization of this thing right here. And these groups have Hecke operators that are q-dependent generalizations of the Hecke operators that these groups have. And I think we've alluded to this already. We just have to remind ourselves what it is that we're talking about here. So what I'm trying to remind us of is that it's a surprising fact that the geometry that's associated with this kind of groups has relationship classification problems that actually have the same classification as the relationship classification problems for this group. So I guess the point is, right, the point is that the Hecke operators that we've been talking about here, we've been saying that what we're doing is we're looking at the relationships between flags on finite sets. But over here, this is a symmetry group not of a finite set, but of a finite vector space over a finite field. And the concept of flag makes sense there as well. And when you classify the relationships, the binary relationships between flags in this geometry, you get, surprisingly, the same classification that you get for the classification of the binary relationships between flags up here. So the classification up here is by Young diagrams. I didn't say that right.
That's the relation of them.
Sorry, I said level set. Okay. I'm trying to fix what I was saying. So first of all, there's the classification of the flags themselves, and then second of all, there's the classification of the relationships between the flags. So the types of flags themselves are something they call partial flags. The classification of the flags is given by the Young diagrams. Let's just remind ourselves of how that works.
Is it true that representations of the two not equal some Hecke algebra have to do with the non-symmetric plane or non-symmetric space?
Yeah.
So let's see. So this is in a Young diagram, so it represents a type of partial flag. So for example, on a finite set, the way I usually interpret this Young diagram, it's telling us, I guess this particular one is telling us that we're going to have, so we have 1, 2, 3, 4, 5, 6. So we have a 6-element set, and we sort of have a let me call it this element set S. In fact, I'll call it S6.
No.
Torture people to use.
I don't know what these are thinking. Okay, so,
How about putting it 6?
well, I just want to say that there's,
Call it SIS.
okay. So there's going to be like A contained in, A contained in B, contained in C, contained in D. I guess D is going to be type 6.
No, C should be 2.
Okay. I start from the. I guess I'll start from the small one. No. Okay. Start from the small one. Size 0.
Oh.
Then size 3. Then size 5.
What happened to 1?
No, he's doing the other way.
What?
Yeah, okay, maybe I should. First of all, maybe I should do an untoned Young diagram.
Oh, okay. Okay, sorry.
And now I'm not so sure which order it's actually going. Well, I guess, okay. Going from top to bottom. Okay, I guess I'll do it like this. We have A, B, C. Okay. So A is everything that's below the bottom. There's nothing below the bottom. B is everything that's below this line. So there's 2 of them. C is everything that's below there, so there's 3. And then D is everything that's below there, so it's 6. You have this flag of subsets. And, so we sort of have plateaus that you sort of achieve. There's, the complete failures, and then people who are a little bit successful, more successful, and more successful. But you can also sort of separate out into grades, right? You can think of it as like, instead of looking at the cumulative totals, which are 0, 2, 3, 6, you can also look at the exact amount at each level, which is 2, 1, 3. But they're just different ways of keeping track of the same information. And the point is that as long as you're dealing with finite sets, it doesn't make a lot of difference which way you think of the flag. You can think of it in a lot of different ways. But there's a generalization of this concept of flag on a vector space. And there you really sort of have to keep track of things a little bit more delicately. So it's really important to remember that a flag of this type, a partial flag of this type on a 6-dimensional vector space consists of picking out a 0-dimensional subspace, which you don't have very much choice about which one to pick, and then picking a 2-dimensional subspace that enlarges that, and then picking a 3-dimensional subspace that enlarges that, and then picking a 6-dimensional subspace that enlarges that. And again, you don't have very much choice about which one to pick up here. There's only one 6-dimensional subspace of a 6-dimensional space. So, right, I'm trying to remind us, particularly myself, how Young diagrams can be used to describe, represent types of partial flags, not just on a finite set, but on a finite-dimensional vector space. And then, these matrices, for example, or these braids, can be used to represent the relationships between the flags. And that works, for the binary relationships between the flags, that works the same way, surprisingly, for the flags on the finite-dimensional vector spaces as it does for the flags on the finite set. And moreover, there's a Q parameter floating around. Q is the cardinality of the field that you're working over. And for bizarre reasons, we pretend that Q is equal to 1 when you're not working over a field, but in fact you're working with finite sets instead of finite vector space. And yes, so in this game of relationships between flags, or in other words, Hecke operators between flag representations, there is this q parameter floating around. And this braid notation suggests stuff about the theory of braids and knots. And there's a perhaps different q parameter floating around in the world of braids and knots. And what's supposed to be suggestive about the braid notation is that you're supposed to think, hey, maybe those q's are really the same thing, and they really are. In some, they really want to be the same q parameter, which is very strange, because I think John has been emphasizing that in this game over here, in the game of relationships between flags and flag geometry, q represents the cardinality of a finite field. Whereas in the theory of braids and knots, there are all sorts of things that people do with the variable q, things that involve things like setting it equal to a root of unity, complex root of unity, which on face it sounds like a very different kind of number from the cardinality of a finite field. So there are weird things going on here. But weird enough that they may be worthwhile to try to track them down and figure out what's going on.
So that's how you get what is like your phase information. You said Q
Again, I'm not quite sure how to respond to that. Maybe. I'll have to try to think about what you're saying. Yes.
Yeah, so I mean, yeah, in a lot
I'll
of
let John
times,
say it.
in this knot theory game, it's good to think of Q as being a phase, and you think of one particle going around another, that picture down there at the bottom, as resulting in a non-trivial phase being acquired by that quantum system. And there's a concept, not just of bosons or fermions, but of anyons in physics of particles that are moving around on a plane. If one wanders around another, you can pick up not a phase plus or minus one, but of any unit.
Is this anyons also pronounced anions? So there is, I've heard something.
Yeah, that's true, but not anyone.
What you're saying is anions are basically anyons.
I think people pronounce the word any in several ways. I'm just pronouncing the word any the way I normally do it.
No, there's
Maybe pronounce it
and yon.
No, it's from the word any.
Okay,
It's a joke.
Okay.
So
You mean any orientation, like you don't make a straight on or like a specific.
Q can be anything, not just plus or minus one, but any.
Okay. Okay, I mean, again, I'm not sure I understood everything Don was saying there. It sounded very interesting, but I would have to know all that. Well, I might know it, but some different language in the center page section. So, I guess what I've been saying here is just a hint, really. This is something that we really are planning to do. We really are planning to develop the theory of the Hecke operators between flag representations, not just for the group 13 bang and n bang in general, but for these other groups. And notice that when you start talking about flag geometry, in this case, it really does start feeling a lot more geometric than it does in this case. In this case, you know, when I go around saying, oh, you should think of these Hecke operators as representing geometric relationships, it feels a little bit funny because it doesn't feel very geometric to some people. But when you start doing this version of the game, you know, you find out that you're working with projective geometry, and it really does very literally start to feel like geometric relationships that you're studying. So the Hecke operators really feel more like geometric relationships when you start doing something with it. And
geometry is the q-deformation of finite set theory?
I don't know. I don't know. But yeah, but as the geometry becomes more like real projective geometry, this parameter q will enter the game in interesting ways. And in interesting ways that relate to the role of the parameter q, in knot theory, in knot invariants, like the Jones invariant.
Where you're using Q as like your variable for the Jones polynomial.
Exactly, right, exactly. So this is just a couple of hints that I'm dropping about how we're planning to proceed. Now the thing I want to do next is I want to specialize this braid notation to a special case that we run into before. And I want to show how this braid notation is secretly equivalent to another notation that John introduced for how to represent certain relationships between flags. So I'll try that now. Okay, so the special case that I'm going to introduce, unfortunately, this example that I've drawn here actually is an example of a special case, unfortunately. The special case I'm going to introduce is the case where on the bottom of the braid, there are exactly two clumps, which I guess corresponds to, I guess that means that this matrix could have
2 rows?
2 rows. Yeah, I think that's right. Yeah, 2 rows. So, but to dramatize that instance, I'll certainly need some examples where we have more than 2 columns. So that's what I'll draw over here. Yeah, more than 2 columns. I'm still a little bit afraid of big numbers. I'll just do 3 columns. Again. All right. I'll just use sort of random names. Or wait a minute. Let me think here. I guess I should actually try to pick which example to do on the basis of trying to get it to agree with the examples that John was doing. So I should think about that for a second. So the examples that Don was talking about he was talking about projective geometry. He was saying projective 3-dimensional geometry. Is that right?
So this 4 choose 2 example that I
Yeah.
see into the ground, so that's about like 1-dimensional subspace with 3-dimensional projective space.
So that, okay, so I should say that's 4 choose 2. What does that mean? So that means we're looking at 4-dimensional
So we're comparing a flag, kind of Grassmannian type, that's a 2-row Young diagram, so a total flag, which is a 4-row Young diagram.
That's what we're doing. Maybe it's supposed to be, maybe supposed to be 4?
Yeah, I think it's four.
And maybe the total in each column is just like 1 or something like that? All right.
I know it's 4 by 2, right, because we're comparing total flags, which have the tall, skinny gut diagram of height 4, to,
Think of it in terms of sets. That's the same picture, the binary relationships are the same.
okay,
A total flag in a set is exactly 1, 1, 1, 1.
Yeah, so, right, so is that what we're doing? We're comparing total flags to,
Say an ordered pair of
partial flags that are just
let's say 2 points or something.
I thought it was just a line.
a line, but yes, that's choosing 2 out
Yes,
of
it's
4.
1, 1, 1, and 2 and 2. So the rows are numbered 2 and 2.
It's again diagram 2 and 2.
Yeah,
The rows, you can label the rows 2 and 2.
yeah.
In that thing that you just drawn there. This is what, if you look at it in terms of finite sets, it's the same way the binary relationships are the same. So,
I mean, you know it has to have the 4.
yes, that's true.
So this is what it is?
Yes.
And
The different stuff.
and we got 6 of these, is that right?
Or choose 2 of them, yeah.
Yes.
And I wrote them as matrices in row echelon form,
Yes.
and I wrote them as
That's really what
all this other thing.
This is really what it is. You've said it. Yes, 4 plus 2.
Oh, you're rude.
Well, except that where we have
Sure,
those
stars
are,
become one.
we're not gonna have, we're gonna know what those are now because we're gonna limit ourselves to final set. Are we not?
Yeah, sure.
So what are the 6 possibilities here? Can you figure out what it is?
It's a random
Like
order.
this one.
Well,
It's a random order.
Well, so this one has, I
we
mean,
don't need to worry about the first row, and then the second row is automatically 6 because every column comes first.
yeah, yeah.
Put 6 different ones, pairs of ones in there, that's it, yeah.
Yeah, right, this is some fairly random order that I'm listing them in.
Well, yes, fine. So, scientific, the first one way of looking at it.
Yeah, you pointed out right, the second row is sort of forced by the first row. There's strange about column sum. Yeah, so I guess we're just taking that process of getting the braid picture from the matrix picture, and I'm doing it in these examples over here. So I guess that means that, for example, my first one will look like, well, so, right, 2 clumps on bottom. And each clump is 2 dots. And then on top, each dot is its own clump. So yeah, I'm trying to get individual names here. A, B, C, D, E, F. Just so I can put clumps here. A, B, C, D, E, F.
So 4 vertical lines.
They're just perfectly vertical in this case. There.
I mean, these are the cases that.
A next to E.
No, it's the 6 that you draw are the ones in between these, right? That's it.
I'm trying to do this one right now. I didn't understand.
Because we're getting one of these pictures for each one of these matrices. So,
Yeah.
yeah, there's one braid for each matrix. So, yeah, and, yeah, so, yeah, that's that one.
Oh, yeah, yeah.
With the convention that
Yes,
we could have twisted the first two, and we could have twisted the second two,
Yes.
and we wouldn't know the difference.
Yes.
So let me try the second one. Let me try the second one. Second one is.
So the A goes to E,
Yeah.
the B goes to F, and the C comes over to E, and then D goes down.
And I did try to go it left over right way. Okay. So there's the picture for that second example. Now I'm trying to connect this to the notation that John introduced here. And when John introduced this notation, I forget exactly how apologetic he was about it. Because there is something to be apologetic about here, which is that we're doing something very confusing. And it's so confusing that, it's sort of questionable, can you draw attention to it or not? If you draw attention to it, we may just get everybody, especially ourselves, confused. Well, that's what we're doing. We're drawing attention to it at the moment. So the notation that John introduced for representing these relationships is he introduced a kind of Young diagram. And the reason that's so confusing is because I got horrible level clip, as I thought. So the Young diagrams, the reason we introduced them in the first place was to represent these kind of flags, kind of partial flags. And then we had this concept of relationships between flags. And now we're using Young diagrams in a different way to represent relationships between flags. And these could be in your notes somewhere, that we actually represented certain relationships between flags by Young diagrams. So I'm kind of there's a Young diagram in this picture. And where's the Young diagram? Should be able to see it. It's like, I'm going to do one more example here to try to bring up, I'm rushing here. I'm going to do one more example that I hope will make it clear where the Young diagrams are hidden in this picture. I'm going to do this example down here. Now, try and tell me if I did this one right. I think this should be the one that goes like.
It doesn't matter. You can draw either one of them. That's fine.
Yeah. No. Actually, you're supposed to do it this way.
Why?
Because again, these guys. The rule is that when these guys are the same clump, you shouldn't put anything. You shouldn't put any information to the picture that makes it seem like one of these guys switch places with one. That's what you meant.
By not putting the cross there, we're
Yeah.
making sure we don't put extra information there.
Yes, that's right. That's right. So in this picture, you can see there are 4 crossings. I forgot to make them left over right, but perhaps think of them as left over right. And those 4 crossings you should think of as forming this Young diagram. Over here, there's just this one crossing. So this sort of represents this Young diagram. It looks like this. It's got one of the 4 boxes. This has all 4 of the boxes. This one up here is the one with no boxes. There are no crossings. The boxes, if you took it to find this picture of these young diagrams, the boxes and them.
When we were doing the Pascal's triangle.
Yeah, is that right?
Yeah, in Pascal's triangle, we were getting these tilted-looking young diagrams.
Yeah. And I'm finding we're doing the same thing here, and I'm relating those young diagram pictures to these braid pictures in this special case.
Crossing by the center of the box.
Yeah, exactly. Crossing to the center of the boxes. I haven't had enough time to try and draw it neater than that or say it neater than that. It's kind of mostly finished right here.